make me feel to make some disclaimers to begin with. First of all, it's my opinions, not red hat. I'm really lazy at create slides that look okay. I found this, I like it, I took it. Pretty much all the stack was created by having multiple bad pizzas at multiple places that had like reviews that says the best pizza at that place, at whatever. So that's what started. Who am I? I'm a Brazilian Pythonista that moved to Scotland for the weather. To be honest, I'm from São Paulo, a 20 million people city. So I moved from this into Dundee, 140,000 people. The fourth largest megalopolis in Scotland, home of the Dundee cake and the birthplace of the marmalade. So again, from this into this, that's 2 minutes away walk from my place, so just around the corner. I'd like to define what is a good place to eat, but I'm not. We all know what it is. This talk is not about that. This talk is about, like, you can go to any first place in any restaurant site, review, it's gonna be nice. But I'm worried, I wanna know about what the 119th or the 314th sites are. And that's what this site's about, is how to find them. The first idea would be like stars and ratings. And if you get something like this, what does this tell us? Well, pretty much nothing. Is the first restaurant a McDonald's or a very good Pinterest place? So we really don't have to judge that. Also, if it is a McDonald's, you get like 5 stars for a lot of people, it might be an interesting McDonald's to see, it might be the best one. So what does that tell us is just that restaurant A, Scarrow likes a little bit more restaurant A than Peter Sam likes restaurant B. Ratings just not solve it. And all the rating sites found that really early on. As any kid just from kindergarten would say that ratings is not gonna work. You have to use the lower bound of Wilson score confidence interval for a Bernoulli parameter, of course. So another good metric that we might try is number distribution of ratings. So if you get that, it fitted. And for the first restaurant, you have like pretty much 4 reviews. It might be good, but it's not nearly enough to know that. For the second restaurant, you got what's called a J-shaped curve, what they call the Ajay, where you have a lot of terrible reviews, a lot of excellent reviews. The thing is, people tend to vote for the very good and the very bad, and the average just, you won't vote, it was all right. So that helps, but doesn't solve the problem. So now for something completely different. Linear algebra. When is that true? Yes, dirty clothes. So washing and drying and washing our dirty clothes does not commute. That's an example from Wikipedia. They make me write that. But yes, matrix multiplication also between after home short. So a funny thing about matrix multiplications is that depending on the order that you do, that's pretty much all the math that you're gonna need for this talk. You get different results with different dimensions. And that's pretty much based on the order that is. So the trick here is that in order to multiply two matrices, the middle values, that is, the columns for the first matrix and the rows for the second one have to be the same number. And the thing is, when you multiply them, they pretty much vanish. You might as well use a pizza emoji and that's gonna disappear. So that's something really nice. Back to São Paulo. São Paulo had a lot of immigrants. In the turn of the 19th century, it was the population of the city, 35% were Italians, 11% were Portuguese. That's almost 50% of immigrants in the turn of the century. When we got close to 1940, it was almost 700,000 Italians, a lot of Moldovs. At that time, this is for the state, the second one for the state, it couldn't find for the city. But, I didn't start my timer on the correct time. That's nice. But the population at São Paulo at that time was less than 1 million people. So there's a lot of Italians there and a lot of immigrants there that create a subculture, a food subculture, pretty much close to what you have in Italy as well with in New York, like the New York style pizza. We do have a São Paulo style pizza. And that's important because it comes to my hypothesis that people that have the same background judge food using the same standards. If you have a culture of something, you're gonna judge all of you have the same culture, you're gonna judge it the same. If you don't have it, you're gonna judge it different. And here's me trying to prove it. That place, the first one, it's not even the top places. I've never been there, but look how tight the Gaussian is. People agree quite well that it's a good pizza. If it was a big pizza, it's gonna be lower, but it's gonna be as tight as well. The second one is the best pizza place in Dundee. And it's awful. But look how dispersed the Gaussian is. And Dundee has 10% of people from abroad. And each one has a different idea what a good pizza is, and don't have a pizza that's defined by Dundee. The same thing happens here in Bilbao. The first one is just, it's not even, again, I like the middle ones. This is the first restaurant that I went here in Bilbao, and it's a solid 4. But again, a very tight Gaussian. A lot of people know that's a 4, and they vote for 4. The tail end in Edinburgh, it's a fish and chip place, and people there have a cult of fish and chips. And also, very tight Gaussian that you have from like people that would not. Thus, proving my hypothesis. Well, it's not really a talk about data science. This is just a yak shave. I don't want to go in the Gaussian rampage, analyze rampage. So this is just based on a hunch. And this is the hunch. That what constitutes a good place to eat is based on individual background. And that's deeply based on the individual makes that if you agree with multiple reviews from someone, you tend to, the chance that you're gonna like another restaurant that they like will be much more likely. And then we go back to linear algebra. Now food. Suppose that I have this, I got it somewhere for a friend, a huge list of users that gave an amount of stars for a restaurant. And I have a huge list of those. Say I have for the 500 top restaurants in Bilbao, for example. What could I do with that? Of course, load in a matrix. And I create a matrix that is restaurants for each row, users for each column, and the value in the middle, value for each position is just how many stars they gave it. And we call it M, just M has dimensions, restaurant and users. So the same way that we could remove dimensions, we can also create them. So if I have a matrix and I want to create 2 new matrices out of there, if I can make that equality, I can generate any size that I want with this extra dimension that I'm creating. And that's quite useful because suppose that I create a matrix that's really an approximation of matrix C. There's an approximation of that matrix users that I got from real data. But this is theoretical one. I created that. And that one is the result of users, or a matrix of restaurants with some categories that I choose, and a matrix of users with the same number of categories. If I can multiply them and create a matrix C, that again, it's a good approximation of matrix M, I can pretty much classify the restaurants and the users in these categories. And that's pretty much what non-negative matrix factorization is. It's a way to create weights for automatically generated categories. You don't know what each category is from beforehand. Sometimes they don't even make sense, but sometimes you can get pretty much a rough approximation what they are. And our results is pretty much a matrix for restaurants that can tell me, oh, this restaurant has these categories in different weights. And I can try to match those to other restaurants and try to find restaurants that I might like based on that one that I like. Oops. I should have done that. So the non-negative part of it, and that's something I should have said, it's just if you keep it all positive, or greater or equal to 0, it facilitates a lot of the ways of generating C. Because one of the most usual ways of doing that, it's the least squares. And that's going to be easier if you do just with positives ones. In our case, we're good because stars are 0 to 5. So how do you generate C? This is taken from this book, this Programming the Collective Intelligence. It's a slightly older book. I guess it's 2010, probably. But it's one of those great books that when you return to them from time to time, you find different stuff. It's all done in Python. It's probably one of the most fun books you're going to have in your bookshelf. So this is just pretty much his algorithm for that, and I just left the comments because that's pretty much all you have, all you need. So first you start RNU with just random values, and then you start iterating. And for each iteration, you calculate how different C and M are. And then if they are the same, you just exit, but that's never, doesn't happen to like real life data. But then you fixate one of the matrices and integrate the weights for the other one. Then you fixate the other ones and try to upgrade the index for the weights for this one. Calculate again, and try to improve it and see what you get. And that's pretty much how I got here. So wait, I have to click here. This is the hard part because I can't, I have no view from here. So this is pretty much like a proof of concept, what I did. This pretty much just loads a bunch of imports. Am I focused in the right place? And this loads the data that I got. No, it didn't. Okay. If I want to run the no negative matrix factorization, just runs on here. But I've just run it. So I got an M matrix that's, oh shoot. Okay. So it is 11,000 users long and 500 deep. From that, I got the restaurant matrix. This is just the bottom of it, with the categories and weights that they have, and also the weights for the users. So if you look at here, you see that user 0 voted for 4 for restaurant 0, and so forth. There's a 5 here. This is a very sparse matrix. And the more connectivity that you have, the better results that you have. And makes sense, like you try to find people that vote likewise for all the restaurants. If you have like just someone just voted once, it's not going to help your data that much. Here I do a little bit of the prettifying of that. So, okay. So, pretty matrix. So this is the restaurant 1. So I have restaurants here. Each of the factors, their row, the URL, and that goes on for 500 for the 500 restaurants. Here I have the users. I've just transposed the matrix so it does make it more likely. How are we in time? Sorry. Okay. Okay. Okay, nice. I didn't start my timer. So here's, again, users' ratings. A lot of them is just like people that voted once, so they don't really influence stuff. Someone with an empty name that I found that just goes here. And here I do have some pandas magic to get people and show them. Can get a little bit back to this, but thing is, I get the restaurant that I like. And this is how they look. No. Come on, scroll. Okay. I should have disabled controls, yes. Okay, so here's how they look. So it has a huge factor 4, which we don't know what it is. A larger factor 0 and factor 3. And that's pretty much it. So we might want to find similar restaurants. So this is just the basic find similar that I found. It's very trivial. It's not even the best way. The best way is probably using some linear programming to find it, reducing the difference. But here I have an indice, which is a solid 4. It has a little bit of 0 here, but you can't see it because the 4 is like 40. So it's huge 4. And from that, you can get an idea what that category might be, because they sell cold tapas, cold pinchos, and croquetas on top of toast. So that might be an indication of croquetas on top of toast kind of marker. Casco, also huge 4, and a large F0 as well. Well, that might be an interesting restaurant to see. It doesn't have that much F3. The same restaurant, that's a good one. And La Deliciosa. And that's a weird one because I first look at it, it didn't seem that interesting, but that's something that it has a huge 4, it has a good F0, some F1 and F2. So that's something that this program, this way of thinking just suggests a new place to look at. El huevo frito, that I didn't look at. This is just searching the similarity between the curves on the factors on the same on the restaurant data. You can also do that through the users. You have factors here that are correlated to some factors. So if I find who voted a lot for factor 4, might be people that like this kind of factor 4 restaurants, and they might be interested to find what they like. So I got some users, this Maxty, this P63. P63 votes a lot for F0, F3, and F4. That might be an interesting person to see. What else they voted for? Arizonate and this kind of stuff. And then from them, you can try to find familiar restaurants that people like. And again, Irinzini, Café Bar Bilbao, that's a different one. It's Socoberia, Casco again, Rioja. And that's it. Alta. Oh, no. Okay. No focus. What? Sorry. It went back to the beginning. Is it changing? It stopped following. Oh, thank you. Okay. Oh yeah, no, it's the right place, sorry. And that's it, thank you. Questions?
Hi. You ended up with 9 categories in your example. Was this by chance, or what was this?
Sorry?
You ended up with 9 categories or so.
Oh, it's F0 to F9, so it's 10 categories. Oh, I chose 10. It's just a random value. I tried with 20. It got the results. The more categories you add, the closer they get to the more similar the matrices are. But also, it makes it harder for search and makes less sense of each category. I got a balance about this. I tried with 5, and I tried with 20. And pretty much 10 was like the sweet spot, and that's pretty much what I used. When you run it, I don't know if I showed there, I was about to, oh, sorry. Here. Oh, come on. Wait. Oh, let's see. Cell type markdown. Did it? Oh, not markdown. Stupid. So yeah, I can get the next. Go away. Code. Yeah. So this is 30 interactions, 50 interactions, sorry. Oh, it's not math. How is it called? Oh, just M. Not that. Totally not that. So they are calculating it. Should be outputting something in a while. So it's a star, so let it calculate. But I'm going to show you how it shows. More questions? Thank you. Oh, sorry. Oh, there's one question.
So, having done all that, is it true that you can sort of tell how much you're going to like a certain restaurant just by looking at the shape of the, you know, if you just go on Google reviews or something like that? I know that I've been walking with you and I see you do that. Yeah. You just say, oh yeah, this one looks good. Just by quickly looking at it, you get a feel for.
Yeah. Just the shapes, the general shape of it can tell you if it is a good. It's a huge from looking at the shape, you can clearly see if you got the J shaped, and depending on how large is the terrible one. It could be an indication that there's a lot of average and poor ratings that you're not seeing. So that's something that I try to avoid. Seeing as close as we can see to a tight Gaussian, it's usually a good sign. But even though a large one might mean just that the restaurant is not really stable, really doesn't always do stuff to the same standard. So even though it might be an interesting or not place to see, but it does tell you some stuff. It is still running. Okay. Thank you. Just over here, I can just so yeah. So wait, do not. Here's how they do, the results come from. This is the difference, and as it goes, it reduces until it doesn't reduce anymore. And that's pretty much the amount of difference that I have between my C matrix, that is the theoretical one, to the actual one. So with 5, that thing doesn't go that low. With 20, it does, but not that much, and doesn't improve the results that much, from what I saw. Again, not data science, it's just a guy with a computer and trying to find places to it. Thank you. Sure. What's the question? Thank you, Jill.